Let's do another Laplace transform problem that's a little bit more involved. Let's see if we can do one that has a unit step function, a piecewise continuous forcing function. So let's look at something like number 69 on page 280. Number 69 pen page 280 again has that piecewise continuous forcing function on the right hand side. So we got y of double prime plus y equals 0. If t is less than pi, it's 1. If t is between pi and 2 pi, and it's 0 if t is greater than or equal to 2 pi. Now remember, before we take the Laplace transform here, we need to rewrite the right-hand side as in terms of unit step functions. It starts at 0 and it bumps up to 1. So the first part will just be the unit step function of t minus pi. So it bumps up to 1 at pi. And then we'll need to subtract off the unit step function of t minus 2 pi because we need to subtract it down to be back at 0 when we get to 2 pi. All right, notice that to take the Laplace transform here, we will look at, or sorry, I need to tell you the initial conditions on this problem too, don't I? Sorry. Y of 0 is 0, and y prime of 0 is 1. Do the Laplace transform on the left-hand side, just like we did in the previous problem. S squared f of s minus s f of little f of 0 minus f prime of 0 plus f of s on the left-hand side. On the right-hand side, we have to make use of the Laplace transforms of these things. So remember, the unit step function shifts our Laplace transform with that e to the negative sa factor, where a is this number that's being subtracted here. So in this case, for this one, the a would be pi. For this one, the a would be 2 pi. The function we're doing the Laplace transform of here is just 1, and it's also just 1 here. So those are, remember, the Laplace transform of 1 is 1 over s. So in this case, we would have e to the minus s pi over s minus e to the minus 2 s pi over s. Our initial conditions say that the function value at 0 is 0. The derivative is 1, so we'll get rid of that. We get, solving this for f of s, again, we have f of s times s squared plus 1. Those are the terms that have an f of s on it. This is 1. We need to add it to the right-hand side. So we have 1 plus e to the minus s pi over s minus e to the minus 2s pi over s. And again, need to divide that over. We're not going to worry about simplifying things because we're going to let GeoGebra do all the heavy lifting for us, handle the inverse Laplace transforms for us. So we've got the right-hand side. We're going to flip over to GeoGebra and type that in on the right-hand side. So again, we want to use inverse Laplace. So I'm going to scroll down and grab it. The top again was 1 plus e to the negative pi times s over s and minus e to the negative 2 pi times s over s. And the denominator was s squared plus 1. So notice that for this particular problem, didn't bother simplifying anything again, just like I did when we did in the previous problem. Didn't simplify anything, and GeoGebra can do the heavy lifting for us. We should be able to do the heavy lifting for us. I don't know why it's not going. Why are you not going? Let's try this again. Inverse Laplace of, we had 1 minus e to the negative, I'm going to write it as s times pi. Now let me just actually put the multiplication sign in there just in case it was having issues with that. Divided by s, that was a plus in front, wasn't it? Change it back over to a plus. And then minus e to the negative 2s do the times pi again, divided by s, and then we need the whole thing divided by s squared plus 1. There it goes. Remember again, I don't know why I didn't do it the first time. I'm guessing it's because I didn't have that multiplication symbol between the pi and the s. So make sure that you define that multiplying. I don't know why I didn't use the space, but it didn't in that case. Remember again where it says heavy side? Here where it says the heavy side function, that's our unit step function. Here it is as well. Now, one of the reasons why we're not seeing the t minus pi in here and the t minus 2 pi in here is because GeoGebra is using the periodicity of the functions to simplify. This would have been 1 minus cosine of t minus pi, and then when cosine of t minus pi is the same thing as the negative of cosine of t, and then the same thing here. Cosine of t minus 2 pi is the same thing as cosine of t because the period's 2 pi. So we write our solution then using the unit step functions. We would have, we've got f of t is equal to, and I've already forgotten what it was. It was sine of t plus 1 plus cosine of t times unit step function of t minus pi. And then I believe it was 1 plus 1, negative 1 plus cosine of t times unit step function of t minus 2 pi. Let me double check that. Yeah, that was the solution. So there it gives us our solution. So remember again, with unit step function, we get that e to the negative pi, sa part in there, where the a is what's been shifted. We have to be a little bit more careful when we have a function that's not just a constant, and we'll do an example of that here in the next video.